about the influence of the rotation of the properties on the properties of strange quark stars. I'm co-working with Dorota Gunde-Kosińska, Loic Villon, and Markus Hansorg. And yes, so from the very beginning. Of course, I will repeat myself a little bit because I'm doing mostly more or less the same what my friends Anya and Marcin. But first, that we know that neutron stars are born from stars which initial masses range from 9 to 40 solar masses, and they reach mass up to more or less 2 solar masses with radius 10 to 30 kilometers, and we can see how dense they are from their mass and size. It's about 10 to the 14 gram per cubic centimeters, and it's comparable to the density of atomic nucleus. They are the most dense objects we know, and the fastest rotating objects in the universe, and they also have very, very high magnetic fields, from 10 to the 9 to 10 to the 15 Gausses. What about their equation of state? Of course, we have no idea what is the real equation of state. Last week we had this conference, and there are many possibilities. People think that that strange stars doesn't exist, but we think that they are, and it's a little bit messy, but we still don't know. So we have to check every possible theory, hypothesis, what could build, what matter is building neutron stars. So here is very very popular picture of some possible equation of states from Weber, and this is neutron stars with fixed mass, 1.4 solar masses, and 10 kilometers radius. And here we have strange stars. So the stars I'm dealing with, and also I'm dealing with bare strange stars, so without crust. So this is very important. So strange quark matter consists of up-down and strange quarks in the same, more or less the same amount, with a little bit additions of electrons. And this three-flavored quark matter has the lowest energy per baryon, even lowest than Arium-56. So it makes that matter the most stable matter in the universe. So normal nuclei would decrease their energy in phase transition in terms of neutron stars and in early universe. So how does the equation of state look like? We have very, very simple equation of state, linear equation of state. Dependence, pressure of density. It's very, very simple. Here we have, of course, pressure, density on some in some point in the star. Here we have rho 0, so the density at the surface of the star, and this is fixed sound velocity in this matter. We're using the simplest MIT back model, where we have massless strange quark, and this A parameter is 1/3. Rho 0 has the value like that. So this is the short history of strange stars. I will briefly just read that. In 1971, Bolmer hypothesis of quark matter, that it could be a ground state of matter. 1984, Witten first calculations, first hypothesis of quark stars. Then 1986, at the same time, Hansel and Alcock, first static models of strange quark stars. 1999, Gurgelon and Stargilast, first fully relativistic calculations of uniformly rotating strange stars for MIT back model. a year ago for day model by Gontek-Rosińska and Bombaci, and I'm sorry, but this is not a proper date. It will be soon in 2014. I hope me and my supervisor Dorota Gontek-Rosińska will release our paper about first fully relativistic calculations of differential rotating strange quark stars described by MIT back model. How the comparison looks like for strange quark stars and neutron stars. Here we have, of course, everybody knows that, that plot. So this is mass and radius. With the blue lines we have neutron stars, and with the green lines we have strange stars. And we can see that strange star doesn't have maximum, minimum mass or minimum radii. And they could, last week it was some kind of discussion about that we can get from observation soon a radius of a neutron star, and that there is a problem that if we have here some radius observed, it will be like a lot of equational state in here. But if we get small radius of neutron star of this object, we can say that maybe for sure it's a strange star, right? So this is density profile in here. For neutron star, for fixed mass 1.3 solar masses, and for strange stars, of course, you don't see this line in here. So we can see that for the same mass, we have smaller radius of those both stars because of the form of matter which builds those both stars. The quark matter is more bound. And here we have also density profile, density and radius for different strange stars with different fixed masses. So we can see that this is the highest mass, almost 2, 0.7 and 0.4. We see here that we have very flat density profile of those stars. So the density is very high at this, in the center and also at the surface. So this is a big problem in numerical calculations. That's why they were performed so much longer, about 20 years after neutron stars, because of numerical problems with that high density jump on the surface. It doesn't work. Okay.
Maybe not.
Try the laptop. There's space on laptop.
I broke it.
Battery is dead.
It doesn't work. Okay.
Try escape and start it again.
It still doesn't work.
Oh. Because mouse pointer go behind the screen.
Thank you. Okay. Now, what about rotation? So, if we have non-rotating stars, we can easily get maximum mass from Oppenheimer-Volkoff equations. But if we have rotation, the stars rotation increases maximum mass. Okay, next. So the rotation leads to the occurrence of other configuration which doesn't exist in case of non-rotating star. Here we have some statistics. Neutron stars. For neutron stars, rigid rotation can increase from 17 to 20% mass. For strange stars, we can have even 44 increase of mass. For rigid rotation, of course. Here we have comparison: strange stars, neutron stars, mass radius dependence. Solid black line is a non-rotating case. Here we have horizontal lines for fixed baryon mass, and we spin up the star. We go. We have in this point. We spin up the star, and we get to the Masted limit or Keplerian limit, if you like. And in this point, we have the last configurations of rotating star, rigidly rotating star, which has its configuration also in static case. But here we have all the space solution of configurations where they don't have where they don't exist in static case. As you can see, for strange stars, we have much more configurations of that kind of configurations. So, as Anya said before, we are using flat star code, which is, if you want for more details, you can go just to this paper. And it uses, we're using a very simple Komatsu rotation law. So this is this parameter. I will tell you in a moment about it. So we have this angular velocity at the center, angular velocity at some point in the star, and this parameter describing degree of differential rotation. But we are using an inverse parameter, so we don't have infinity, and it's described like that. So if this value is equal 0, we don't have differential rotation, we have rigid rotation. And for higher values, we have higher degree of differential rotation. It is very simple because we don't want to, in plans we also have to put other more complicated rotation law. But for now, it is very simple. So we have the maximum, this is angular velocity in function of radius. We have a maximum angular velocity at the surface, in the center, and it decreases with radius. Yes, so how we do our calculations. This is, I will tell you about in a moment about this. So here we start from spherically symmetric configurations, star. We spin up the star, so we increase angular velocity, and we get some few types, different types of stars. So my colleagues told you about 4 types. I will just tell you about 2 types, A and C. So here we have type A with solid line. Of course, this is baryon mass normalized to maximum mass of static case, so non-rotating star. And here we have polar to equatorial radius, polar over equatorial radius ratio. So with solid lines, we have type A, and it is at Masted limit. And with dashed lines, you have type C. So the configuration which goes to values of a ratio to about 0. So this toroidal configurations. I think that's it. And we can see. Okay, so I will tell you about this later. So we also have this. So we have this degree of differential rotation, and we have this value, critical value of degree of differential rotation, which is some kind of a boundary between all those types. And here, this value of critical degree of differential rotation. Here is some parameter which you can, which actually is you can take as a maximum density. And yeah, with green line you have equation of state of polytropes with gamma factor equals 2. With red line you have strange quark stars, and with black line you have incompressible fluid. So as you can see, this boundary, this critical value of this parameter, degree of differential rotation, is much lower than for neutron star. So below that line, red line, you have type A and B, and above you have C and D. And as you can see here easily, that for very low degrees of differential rotation, you have these toroidal configurations. So where this ratio tends to 0. So maximum mass, how does it look? So it's also for A and C type. This is still normalized value of baryon mass. Here you have a non-rotating case. So this is normalized to this point. With solid lines you have type A, so at mass shed limit. With dashed lines you have these toroidal configurations. And what is very important in here, that everybody thought that if we will, oh, no, okay. Okay, everybody thought that if we think about differential rotation, so if we increase differential rotation, we can increase maximum mass. So the higher degree of differential rotation, we can get the higher masses. For type A, it is like that. If we take higher degree of differential rotation, we get higher masses. But it is inverse in type C. If we take higher masses, higher degrees of differential rotation, we get lower maximum masses. And this is very important in those results. So this you should remember. So if we take those points, these are maximum masses in that configurations. If we take those points and put them on this plot, so here is maximum mass, of course normalized, and here we have this degree of differential rotation. With colored line we have polytropic equation of state. With black line we have strange stars. For a given degree of differential rotation, we have the highest increase of mass is for strange stars. About stability, we don't perform hydrodynamical calculations, so we can't say anything about stability. But there is some parameter, J/m², which can say something about stability. If this value is larger than 1, a star could be stabilized by against collapse to a black hole. So here we have this maximum density. Here we have J/m², and we can see that at some density, those configurations value of this parameter is larger than 1. So those configurations could be stabilized by differential rotation against collapse to a black hole. How much time do I have? 2 minutes? 2 minutes? Okay. For static non-rotating star, the maximum density is about here. So it's 0.45, something like that. So I fixed maximum density and calculated for few values of this degree of differential rotation, this J over M squared. So my results are with pink color, and others are from this paper. And as you can see, it looks a little bit different. They didn't have, it's just few, for given configuration is here, it's just few points. They didn't know how it behaves exactly. We show that this is type A and C. How exactly does it look like? It doesn't have that kind of shape like they did it right here in this paper. So, yeah, so this is conclusions. You can read, write, and thank you.